Okay, so on to tonight's main event. So Micheal Lanham will be talking. I won't go through all of this. He's done a lot of things. Uh, we're very excited to have him here. He's been working in this for 20 years, and so we're very excited to see what he has to show on deep learning. So take it away, Micheal.
General, who here does any deep learning now? 2 or 3 hands? Okay, interesting. Okay, so deep learning sort of falls in this area. We often maybe think of sort of the heart of what we consider artificial intelligence, I guess, with data science being on the fringe a little bit. There's even some contention about whether artificial intelligence is even the proper name for some of this stuff, because really some of these deep learning networks are really, once the weights are there and they're trained, it really is just doing the same thing as a data science algorithm. It's just able to handle more data, that's all. Okay, so I just want to get some basics of what is deep learning. So often we see this sort of neuron or biological neuron that we see. Some people compare deep learning to the biological neuron. That doesn't work very well. It is inspired from the neuron, but it doesn't have very much in common with the neuron. So the model we played with was inspired by this sort of network connection piece and stuff like that, but the weights in our brain, they believe, do not work in any ways by strengthening the connections or stuff like that. It works entirely differently, and believe, a lot of people believe that actually most of our learning happens when we sleep at night, and the connections in our brain actually strengthen as we sleep. And it's that process at night, and the reason why we need sleep is to get those strengthening of connections. Okay? So we looked at essentially a basic simple perceptron, just some basic neurons. So that perceptron model that we looked at goes all the way back to somewhere in the 1950s. And then we sort of started building these things into multiple layers in the 90s or so forth. There was a couple decades there where people just lost interest entirely in deep learning. One of them about 1970 and the other around 2000. And then about 2009, 2010, we started to see this stuff and the explosive growth of deep learning for all sorts of applications. Okay, so I mean, we sort of understand the basic concept now. We have an input coming in. The input could be a cat or dog image. So in a network, really what we take is just the pixels, and we feed them as inputs in. So we take the pixel value. It might be just a number from 0 to 1, for instance, on a grayscale channel or something, and that's the value that gets input. So on a typical cat picture or dog picture, it might have thousands of pixels that are going into a single neuron that we're taking the inputs for. Okay? And in a fully connected network, you can see the number of weights can quickly add up, especially when we add multiple layers, like on these examples. So when we start to add all these layers, we get tons of weights and things like that, but we can start to do really powerful things. By taking this data and being able to train it with backpropagation, we can identify different species of animals, for instance, or even different types of animals, or animals doing different things, for instance. Okay, so really why is deep learning sort of becoming such a big hit now? It's been around for almost 80 years, or 70 years, I guess, and really hasn't gone anywhere. In fact, it's been sort of the black sheep of the computer science world for the longest time since I can remember. I've been putting neural networks on my resume for 20 years, and I don't think I've had anybody interested in any sort of neural network stuff since the last 2 years, really. Okay, so really a lot of it comes down to advances in research and just, I guess, computing power in general. And really a lot of it was driven by Geoffrey Hinton's work with the ImageNet challenge. Essentially, they built a network using some CNN, convolutional neural network layers, that essentially breaks the images up from the ImageNet, which is a class of 50 million images that are broken out into 1,000 classes. So imagine a network that breaks out to the end 1,000 different classes. We're feeding 50 million images that has to recognize each one of those classes of image. Very powerful stuff. Okay. Also, scale is sort of driving deep learning progression. So we've all heard about Moore's Law, and who's heard of Moore's Law is going to end in 2020? A few people, right? So the belief is that Moore's Law is going to end in 2020. So that's essentially our computing power doubling every 18 months is going to stop. But there's some thought that maybe it won't. And it's hard to tell. So from 2020 to 2025, there's really some contention on how much the processing power is going to increase and if it's going to increase enough at all. But if it does, that's where this diagram here is going to change dramatically. So this diagram is sort of leveling off on the assumption that Moore's Law is going to sort of level out, essentially. But what we find with deep learning networks is they scale better with the amount of data we throw at them. So for any other sort of data science algorithms, what we generally find is they don't scale as well as the deep learning networks. And I could tell you with building these networks that with some of the power, and if you're using GPUs and stuff like that, they're really, really fast. They're extremely fast. The computing power is just amazing. If I could do anything or everything with a GPU, program everything, I probably would. It's pretty incredible what the GPUs can do. And really, it comes down to them, they're really being built to consume data, right? Essentially, we're just throwing tons of data at these things and throwing them through, training them, and building them, okay? So we've all sort of seen these examples. This is an example of a real-time image capture, looks like a self-driving car, some interpretations of some various things. What's happening here is what we call a YOLO model, so it's you only look once. The network is actually able to identify in this image and put a box around each of the vehicles or things or objects it recognizes. In this case, it's color shading them, again for the same principle. So some pretty powerful stuff. Or transforming data. So here's an example of, this is some transformations across latent spaces, from real images to fake images. This here is living portraits, an example where we've taken portraits and we can now make them do things. In this example, we're making them talk or whatever. Some really powerful stuff. Some more living portraits and other things. So, and new types of learning. What I'm referring to here is the GAN, the Generative Adversarial Network, and Variational Autoencoder. We're getting away with doing these sorts of mapping across latent spaces. Okay, and also challenges to our perceptron. So I didn't really put up the whole video of this, but this is a deep fake. Who here has heard or seen of the deep fakes or the deep news stuff? A number of you. So the University of Waterloo, I think, is still holding a contest for $1 million for anybody that can come up with a way to identify deep, fake news. This is an example of, he's doing essentially the talking, and Obama is sort of doing the talk or doing the talking for him. This was trained on a GAN of, there's tons of faces, tons of images of Obama to train on, so that's how come it works so well in this example. Again, these examples are so powerful because there is a lot of training data. Okay? And then we're sort of opening the door to AGI, or artificial general intelligence. That's where we build an intelligence or a network that can work across tasks. So imagine a network that can sort of play Atari games and do this sort of animation of this person and maybe do this piece here where it's playing ping pong, all from the same thing. That would be sort of a general intelligence piece. It might need some training for each of these pieces, but in general, it would sort of be able to take each of those tasks. We're not anywhere near that right now. We are getting pretty close with deep reinforcement learning. So this is an example of, these two top ones are deep reinforcement learning examples. And then this bottom one is an imitation learning example. So in this bottom one, it's actually learning how to play based on her movements. Okay, so really why? So a lot of it comes down to advances in convolutional neural networks, which was developed by Hinton, 2012. Got a big push. Neural networks and GANs. GANs was developed by in University of Montreal. And then deep reinforcement learning. Who knows where that was sort of founded? So I mentioned two Canadian universities. Who knows the third university where this was founded?
Alberta.
University of Alberta, yeah. Canada is actually a huge leader. Calgary is really pathetic because it is way, way behind the other cities. Ontario is just going crazy for this stuff. It's amazing. But, I mean, there's Hinton, and Sutton's pretty recluse, so I think. So convolutional neural networks. Here's an example of a convolutional neural network. I won't get too much into this, but essentially what we can do with a convolutional neural network is we break the image apart into features, kind of like the same way our human eye learns or identifies things itself. It sort of breaks things into features and then learns those features using this process of convolution, which essentially extracts elements from the image and then pulls them together to extract these features. And we've been really powerful. That's that ImageNet example where we took 50 million images and broke it down to 1,000 classes. There's recurrent neural networks, which process context-sensitive information. So stuff that's time-sensitive, language processing, for instance. So a lot of our current advances in speech recognition or anything to do with translation or Alexa and stuff like that have a lot to do with recurrent neural networks. Okay, and the GAN. So this is an example of the GAN where we're using, in this example, we have a low-res image, a high-res, or sort of a bicubic that's sort of the same thing, and then the GAN is actually coming out with increasing the resolution of the image based on what it sort of thinks it is. So I don't know if anybody sort of remembers, but way back in the first Blade Runner, there's that image where he does a zoom in and he does a pixel enhancement and he zooms in again and he does a pixel enhancement. Well, that's no longer fantasy. That's actually becoming reality with deep learning networks. Okay, and deep reinforcement learning. So here's an example of deep reinforcement learning, Pac-Man. And then this is an example of playing soccer. This is with actually just two different brains. So we have one brain controlling the strikers, so essentially the ones that's scoring, and then one brain controlling goalies. And the brain gets rewarded based on if it scores or gets scored on, essentially.
Michael, they have no knowledge of rules or anything, right?
No. So the only thing in this example, and I guess I'm going kind of light in some of this stuff, right? So in this example, the only thing this understands is just the environment, and the only thing it gets from the environment is just this and a reward. And it gets a reward when it scores. The striker gets a reward when it scores into the net, and the goalkeeper gets a reward when it sort of keeps a goal out. And it gets a negative reward when it gets scored on, I guess, as well. Or another example is this new thing that's come out within the last couple years. I'm going to stop that here because it's called curiosity learning. So what we do is we teach a deep reinforcement learning network sort of the same way we did in the last example. The only thing the network knows is just the environment. So essentially what it can see, and it has these sort of sensors you can see here. And the only thing in the environment are these blocks and a button. Okay? It doesn't receive any reward or anything until it hits the button, and then one of those blocks of things turns gold, and there's a gold box. It has to knock over this and then hit the box. Then it receives the reward. Okay, so it's sort of like a hidden reward essentially. And it normally, with a normal deep reinforcement learning algorithm, or even just a human player, it would almost be impossible to train something on this, but with curiosity. So we train the algorithm to essentially, if it gets surprised, it gets curious, and the more curious it gets, it follows that path. So instead of following the path that it knows very well, it starts to follow the path where it gets surprised on. And this is really powerful because we can start to turn this on to, I mean, this is a game scenario, but we could start to turn this on other forms of data and allow things to sort of discover other things in data, right? Some interesting things. And also different types of intrinsic rewards. So right now we have curiosity, but we could have love, hate, all sorts of other types of things with this intrinsic reward system. Okay, also imitation learning. So I showed an example of this already, but self-driving cars are often done with imitation learning as well. And that's where essentially we're showing the algorithm how to drive or how to play ping pong or something, and the algorithm essentially learns from the same actions. And we can do that because we can essentially push all those actions into a deep learning network. Okay, and here's some more examples of imitation learning where in the top here, we have examples where humans are doing some action and then those actions are equated to the same individual here, and you notice at top that that individual is not wearing any sort of reflectors or anything to identify joints or anything. The networks all learn that just by looking at the pose of the person. And the same thing down here on these examples. Okay, so why oil and gas? So why is this so beneficial to oil and gas? So really, a lot of it comes down to our data availability, and this sort of boggles my mind sometimes, is that we have all this data available, it's all free, and yet we don't really do anything with it. We don't really have a good understanding of it. I often hear people say, well, I'm working on this project, but my data sucks. I don't know how many times I hear that. So deep learning could probably help a little bit with that, but there's sort of other avenues now becoming available with some other services as well. So as an example, who here knows that Google has a new service called data labeling? Anybody? A data labeling service. Nobody. So this data labeling service, essentially, if you have 1,000 images you want someone to label, a human to label, you can give them to Google, they'll charge you $35 and they'll do 1,000 images. They do GIS stuff, they do all sorts of other inputs and types of data. It's really interesting. They have a whole service built around this, and I'm sure others will quickly follow. Some of it has to be, I think, AI-driven or AI-enhanced, I think, because it's $35 for 1,000 images seems pretty cheap to me, but anyways, okay? So, and really it comes back to the deep learning scale piece. Other learning algorithms are just going to sort of level out, and deep learning is really going to continue powering through. It really makes sense for the investment in long term. Even if it's going to take you a while to ramp up, the deep learning is the way to go because computationally it makes the most sense. Okay. It's also very accessible. So here's a number of frameworks and examples that I've shown here. There's a lot of services now as well. I'm actually writing a book on the Google Cloud Provision Service for AI. A lot of it, their service is driven by a lot of their AutoML technology, which I'll talk to it a little bit in the end. But Amazon, Microsoft, Google, missing some people. Who? What? Oh, IBM. Anybody else? There's a few Chinese big players too, but you don't really hear them too often. Okay. And then lots of good deep learning frameworks. Some good ones to use. Most of them are they're not too bad. Like I said, I have a Keras example of that last exercise we did that could probably solve that in 20 lines of code. Okay, and then if you're going to get into this, really the most basic one is the Keras. TensorFlow is sort of has a mixture of both, and then PyTorch is becoming very powerful. A lot of people are using PyTorch now, especially for commercial versions and stuff like that. So this is some examples of coding. So on here, you can see this is an example of a sequential model that's fully connected. And this is the way we would sort of build that model. You can see our activation functions, optimizer, the input types, so 32 input neurons, 1 output neuron, right? So before you started this, you probably wouldn't have understood any of this, but you probably understood a lot more of this than you did when we first started, hopefully. Okay, so applications of deep learning. So I just want to go over a few of the applications. Some of the more common ones like image processing, natural language processing, data discovery, and all that good stuff. Okay? And for oil and gas. Yeah, so this is just going through and talking about each of those applications for oil and gas in a little more detail. Just some quick musings I had. About 10 years ago, I ran a research group for a few years, a global research group, and I would have a lot more ideas on this slide than back if I was still doing that, but I'm not anymore. Okay, so image analysis and classification. Lots of areas for this. Safety issues, for instance, facility management, inspection services, pipeline inspection, obviously. Construction pieces as well. Okay. Natural language processing, again, more safety stuff. I have to try and see what I wrote here. Document indexing. This is a big one. I've worked in a lot in document indexing systems and stuff like that. It really is a big one that people just want to be able to throw their data into a spot and have a machine just tell them where that data is. I'm sure that a lot of document indexing and search services are going to start to really use a lot more deep learning pieces. Okay. Video indexing. Here's another example of applications for safety, obviously, or other applications for automated tracking on a rig, for instance, or other applications that way. In this instance here, somebody jackhammering or on construction. Okay. Reinforcement learning. So this is a big one because it's pretty close to home, U of A. But so we have everything from these examples here to some pretty good examples of reinforcement learning being used, I think, for steam control, I think, in one example, or have been used for steam control in a while now. But other control systems, production optimization, cost optimization is another one, okay? Where you could take a piece of data and say, they're often used for sort of think production optimization if you're looking at sort of values coming through your production system and you know that sort of a threshold that is a good value or not good value, then you could sort of set a reward to the algorithm and the algorithm would just naturally find what those good values are and determine that on its own. Okay, imitation learning. So this is a really big one. It's probably going to take over a lot more of oil and gas manufacturing pieces, I think, in the next few years. We'll see. Task automation, data reanalysis is a big one. Again, production efficiency, managing your data. For us, we use imitation learning where we actually observe the geologists doing their work, and then we sort of observe that, capture that, and we use that as part of our process for learning, which I'll show you in a while here. And reinforcement learning again. Covered that a few times. Okay. Generative adversarial networks. So here's an interesting one where, we could have data that is describing anything. It could be describing a reservoir. It could be describing a wireline log, for instance, or anything like that. You could use that data to then generate either new data or infer something about that data itself. And I'll show you an example here I have of something we built in our software using a GAN. Okay, and like I said, GAN show some particular value. The top one is showing a style GAN where we're applying, or not style, but this is an object GAN. We're actually enhancing the image with various objects. And these are free. You can usually go on and find these types of examples and play with them. But they're getting pretty powerful, these types of things. So the things you used to be able to do in Photoshop, for instance, this is starting to sort of infiltrate that area. So now that you can, you could colorize a photo potentially in a few years with one of these applications. And some other applications where we're sort of redesigning something and then fitting it to a specific design and then finding that as well. It's another example of that. Okay, and then also AutoML. And AutoML is essentially an auto version of machine learning in general, or deep learning in general. I'll say deep learning, deep reinforcement learning. I guess it's being applied to some data science algorithms as well, I think. I'm not sure if it has as many hyperparameters. So this is the next stage of deep learning where instead of having to train or even decide how to compose or build your network or design your network, decide on your inputs or outputs, you can actually sign up to a service and have it done all for you. And Google has this service right now called AutoML Tables, where you can actually take tabular data, feed it into it, and generate and run some AutoML, run it doing deep learning on it, and it can sort of solve whatever problem you're looking at, for instance, and it can give you variations and stuff like that. I believe it uses deep learning. It also has what-if analysis is another powerful one. It can do what-if against deep learning or other types of machine learning algorithms that you're using. Okay, so I just want to finish with some of my experience. So this is a piece of work I did in Unity. Unity has a deep reinforcement learning platform called ML Agents. And what I've done here is I've constructed essentially a wireline log viewer. This is essentially just the gamma. It's developed for a geologist to sort of play this game where they scroll through the log. They can scroll up and down, and they can zoom in and out. Okay, just as if they were in a petrophysics package. And their job is actually to go through and press a space bar to identify a top. So we're training a reinforcement learning algorithm to do the same thing. It's going through and it's going to try and recognize tops. And you can see it actually is able to do that after 50,000 iterations or so. You can see here that it's failing. Red means it's failed, and then green means it's successful. So it successfully learned that. So this example took me about a day to program, and then a week to teach to fix it so that the machine would stop cheating, or the agent or the algorithm would stop cheating. Every time there was a cheat or some way of breaking the simulation, it would find it. It was quite good at it. So the input for this is a deep reinforcement learning algorithm. So the input for this is just the image. The algorithm is seeing exactly the same pixels that the geologist sees. And that's what I'm feeding the algorithm. Okay? Same image is getting fed into the algorithm, and the deep reinforcement learning algorithm, it just gets a reward when it picks the right top. So when it picks that top, you can see it turns green, it's getting a positive reward. If it picks a bad top, it gets a negative reward. And using this, the network that I had to develop on top of this was a pretty heavy convolutional neural networks, which sort of identified the features in the characteristics of the gamma, but then give you a good example of what's going on there. So our next piece was the GeoAgent, and the GeoAgent is a piece we have in our software. This is our software called GeoDirect. And in this software, essentially, we help people horizontally drill wells. This is an example of a horizontal well being drilled. In this particular example, you can see that there's a lot of faulting, and that's quite difficult to predict sometimes. So what we've done is we feed in to the agent 100,000 events from 3,000 different wells, and we train it using a GAN. So the GAN does two things. The generative adversarial network does two things. It generates data, so essentially tries to generate some data that looks like the real thing, and then we have a second network that is sort of like the police that tells the generator if it's wrong or right. Okay, it'll say that doesn't look like the right example, it's wrong, try and fix it. The discriminator, we call it, also learns how to discriminate properly based on real data. So we feed it a bunch of real data, and it's able to discriminate real data versus fake data, and the generator keeps trying to generate real data. That process of working together is how we applied and trained this. And what you see here is this our GeoAgent track is right here. And the GeoAgent's trained to identify and colorize the sections of the cells the geologist is interpreting as green, meaning it's a good pick, or I recognize the pick, or yellow, meaning I don't recognize the pick, or it goes even down to red to say I don't agree with that pick at all. These picks, or this confidence, is essentially trained off the geologists doing all these picks themselves. So what we find is the way these guys are matching up this data and cutting the data and doing these interpretations over 3,000 wells, a deep learning network can make sense of it. And what we found is, even with our first generation, which is getting 89% accuracy, was still pretty good. Our second generation, which is 98% accurate, is conditioned on dogleg severity. And you condition again by introducing some attributes of your training sample. Normally GAN is unsupervised, but when you condition it, you add conditions. And in this case, we'll add dogleg severity, for instance. Any questions on this example?
So your training set is real, is it reverse geosteered wells that have been?
Yeah, it's geosteered wells, yes. Yeah.
So the 100,000 events are horizon picks?
Yes. Yes.
Does the geological context have to be relatively similar over that set of events?
No, so that's a really interesting thing. That's why it's interesting, because we're identifying. You can see in this one spot here, it's sort of yellow, so its confidence is not good, and we would sort of expect that. But in this area, we're green, and that's the area that we're never really sure is, because when you sort of do these faulting and stuff like that, your data sorts to start to stack on top of each other is the problem, and that's understanding how that data stacks on top of each other is really difficult. But the GAN is sort of able to, or shall I say the discriminator part of the GAN is able to sort of discern if it's a sort of a series of cuts or picks that's identified or seen before.
Is there a particular type of well log that's involved here, or most different types? Or
What do you mean by well
are you
log?
looking at the well logs?
Yeah,
The
so
gamma
this,
ray or
yeah, so the only thing we get is gamma,
gamma?
just gamma.
So just that one type of well log.
Just the one type.
Okay.
Yeah.
Did you try this on any synthetic data?
How do you mean synthetic?
So if you took like a vertical gamma ray profile, upscaled it to a model, then steered wells through that, you generate a whole bunch of synthetics.
No, so the generator is not actually up to par. The discriminator works quite well. The generator is not. So we haven't done any. If that's what you mean by synthetic data.
No, I mean more like build a model with a vertical gamma ray profile, drape a few 100,000 or a million well trajectories through it, generate synthetic gamma, and then work out where you want to use that as a thing.
Oh, okay. Yeah. No, we haven't tried that yet. Any other questions? No? Okay, thank you. And any other questions about anything?
I know Kaggle did about a year ago a competition on 3D seismic data interpretation with machine learning. Do you know if any of that's going on in the real world, or?
3D seismic?
Yeah.
Yeah. IBM is doing that, I believe. Yeah. Yeah, IBM is doing a bunch of stuff with 3D, a lot of work in 3D stuff, from what last I heard. Yeah.
As far as I know, Conoco is also doing some waveform reconstruction using similar techniques.
Yeah, yeah. I think seismic interpretation is a big one because you're doing it on images a lot of the time, so it sort of plays well with what's sort of already published. Other data sets, no, not so much. I think people just don't have a good analog to sort of base it on, I think, in a lot of cases. They want a sort of an analog like the image example, right? Anybody else?
Well, thank you very much, Michael.
Thank you.